Hello! So today's little lesson is all about dealing with percent composition. Percent composition should be a relatively straightforward calculation to do. It's one way of analyzing the components of a compound, so trying to figure out if we know the elements that are present in a formula, roughly which elements are more dominant in terms of mass, is basically what we're doing today. So the pretty straightforward calculations, again, you probably want to have a periodic table and a calculator out so that you can kind of do these along with, but this is one of the easier ones that we end up doing. So, all right, so first things first, we're going to be dealing with, my cat's coming to visit, very nice. We're going to be dealing with something called percent composition, which is how we calculate the different components quantitatively as opposed to just qualitatively. You know, quantitatively we have a formula, and that gives us kind of a ratio of like 2 hydrogens to 1 oxygen. But this is in terms of mass, and that's what's a little bit different about this one. We're not looking at the percent composition in terms of number of atoms. We're looking at it as a percent of sort of heaviness, so to speak. So keep in mind that when we're dealing with this, just like any percent, you're always going to use part divided by whole. That's kind of the typical percent formula. And then you always multiply by 100 to get it into that percent format. So in this case, since we're dealing with the percents of different elements and by mass, we're going to be using molar masses. So part divided by whole here is actually the molar mass of each element, and then the whole is going to be the molar mass of the compound when you know the formula. We'll be dealing with some other versions of this later on where we can actually use percent composition to figure out the formula, but we're not going to do that in this lesson. We're going to assume that we know what the formula is here and be able to kind of work from there. So why do we bother doing this? Percent composition is actually a really commonly used analytical technique when you've got a new compound and you're starting to try to figure out exactly what this compound is or how it's put together. One of the first things that you typically do is percent composition. What elements are present? And sort of by mass, how common are each element that's in there? Are they rare? Are they common? Are they heavy? Are they light? So for example, you can actually use this to differentiate between two very similar compounds. Like for example, the ones that I have on the screen here, dopamine and serotonin, these are actually the ones that are very common neurotransmitters, so they're a part of your brain, and they're actually the chemical basis of happiness. That's why it's the two things that you enjoy. But if you take a look at the formula for these two, the way that your brain releases these two compounds took us a long time to figure out that they were actually kind of different, because if you take a look at them, they have the same elements present in them. The black ones represent carbon, the red ones, nice. The red ones are oxygen, blue ones are nitrogen, and the white ones, the little white ones on the outside, are hydrogens. So you can kind of take a look at first glance, they look very similar to each other, but it was through things like chemical percent composition of this chemical compounds that we started to realize that they were slightly different, that one of them had just a little bit more oxygen, a little bit more nitrogen. So even though they look similar, they do have some different technical makeup to them, and then we could start to investigate further what really is it that's separating these two from each other. So here's how the basic calculation works. Again, part divided by whole. Don't make this part too hard. So we're going to take a look at, for example, the percent composition differences between hydrogen oxygen in water versus hydrogen peroxide. So if we start taking the water apart, we get those basic pieces. Those are the masses that you're going to need. So this is kind of my molar mass work, and I always start here. Keep in mind that because we have H2O, we need to multiply the molar mass of hydrogen by 2, because there's 2 hydrogens in each molecule. And then we add them all up. And so by the time you find the molar mass of the compound, you get 18.02. And then we start doing our percent composition. What's the percent of hydrogen? What's the percent of oxygen? So the way I would do this is I would set up the part that is hydrogen, which is 2.02 grams. It's the total of all the hydrogens in there, divided by the molar mass of the whole compound, which is 18. So in this case, if you multiply it out, I didn't show the times 100 because I figure you guys are in high school. At least by now you should be able to handle that part. You get 11.21%. On the calculator it shows 0.1121, but that's 11.21%. If I do it with oxygen, now there's only one oxygen present, so it's 16 divided by 18, 88.79%. Definitely by mass, water is largely oxygen, even though 2/3 of the atoms are hydrogen. How's that for weird, right? So percent composition by mass is 11.2% or so hydrogen and 88.8% oxygen. If you've done it right, they should add up to 100 because it should be 100% when you're done. So if we take a look at hydrogen peroxide, we can see just by doing this percent composition, something a little bit different is going on here. And we find out that we've got 2 hydrogens and 2 oxygens in here. So our molar mass here is a bit heavier. It's 34 grams per mole, roughly, as opposed to just 18. So when we start to redo our calculations here, we can see that the percent of hydrogen actually drops quite a bit. It's still 2.02 grams, but now the molar mass is 34. So the percent of hydrogen in hydrogen peroxide, it's only about 6%. So you can probably do it by subtraction to figure out what oxygen is. Oxygen's about 94%, or it's 32.00 divided by 34.02. So this is how you do these basic calculations of the part, the individual elements, divided by the whole, which is the whole compound. All right, so for you, one of the things that's going to start driving you a little bit nuts is that you do have to memorize or re-memorize maybe your polyatomics and your naming rules, because a lot of times with percent composition, you're just given the name of the formula and then you have to go figure out the formula from there. So, so in this case, like the example I've given to you is the percentage of nickel and nickel 2 chlorate. So this is the time where if you're doing pretty good, you want to hit pause, see if you can work this out, and then I'm going to work it out with you here in just a second. So it's a percentage of nickel in nickel 2 chlorate. You ready? Okay, so I'll start with writing the formula. So nickel's a 2 plus, that's what the nickel 2 means. Chlorate, if you'll remember, ATE, is one of our polyatomics, so it's ElO3, and it has a 1 minus charge. So by the time I finish writing my formula, symbol charge, we got to cross them down. We get this is our final formula. It's important to get the formula right, because other than that you can't have the right molar mass and none of your calculations are going to work out correctly. So this is the formula for nickel chloride, NiClO3 with a parentheses 2 out there. So now we can start doing our masses. In this case, the question asked just for the percentage of nickel, so you don't necessarily have to do the chlorine and the oxygen percentages. This one specifically asked for nickel, so I would do this to get my molar mass. There's 1 nickel that's present, 58.69. There are a total of 2 chlorines present, 35.45 times 2. And again, that's because this 2 outside multiplies across. Remember, it distributes to the chlorines and to the oxygens. So don't forget that when you're doing your molar mass calculations. And then my oxygens, I've got 16.00 times a total of 6. So there's 3 oxygens in each chlorate times 2 chlorates total. So here's our total molar mass, which is 225.59 grams per mole is the total molar mass of nickel. Now the percent composition of the percent of nickel in here, I just need to know how much nickel it is out of how much total it is. So it's this calculation right here, 58.69, which is the mass of the nickel, divided by 225.59, which is the mass of the whole compound, and I get a final answer of 26.02% nickel in there. And yes, you could go through and figure out the percentage of chlorine and the percentage of oxygen, but this particular question just asked about the percent of nickel. There you go. All right. There are some variations on this in terms of what you're going to do. A lot of it's variations in the wording. The basic calculation at the end is going to be the same. You're still doing part, you're still doing whole, you're still dividing times 10% or times 100 to get 100%. That is still exactly the same. It's just the way the wording's on there. So slow down, read the questions correctly, and make sure you kind of know what you're up to. So this one talks about some sort of a compound that's got potassium, chromium, and oxygen. This one's found to be 38.1% oxygen. Was it potassium chromate or potassium dichromate? So yeah, you got to go look back and figure out what your polyatomic ions are, chromate, dichromate. All right, so let's start with this. Here's my strategies that I would implement if I were doing this. Number 1, write the formula, start there. Potassium chromate, potassium dichromate. Number 2, calculate the molar masses of each one, figure out what those are, and then just determine the percentage of oxygen, because this question here is only asking about 31.8% oxygen, so that's going to be the key for me. I don't have to do every single element to get the answer to this. So here's my 2 molar masses. If I write my formulas correctly, potassium chromate is K2CrO4, because chromate has a 2 minus charge. Potassium dichromate is K2Cr2O7. Dichromate is Cr2O7 with a 2 minus charge. So here they are, the molar masses on there. I'll let you go and get your periodic table out and figure out how I got those, but it's just a simple matter of finding the mass of potassium times 2, the mass of chromium times 1 or 2, and the mass of oxygen times either 4 or 7, depending on what it is. And then I'm going to go grab my oxygen masses and figure out what my percent of oxygen is. So my percent of oxygen in potassium chromate is 64 grams out of 194.19. So again, why is it 64? That's 16 times 4, because there's 4 oxygens, and the 194 is the molar mass of potassium chromate. For dichromate, it is 112. Why is it 112? Oxygen times 7, so it's 16 times 7 gives me 112, and then the total molar mass for that's 294.19. So there you got your 2 percentages on there. The percent of oxygen in potassium chromate is 32, roughly 33%. The percent of oxygen in potassium dichromate is 38%. So now I know which of the 2 is going to be correct. Between the 2 that's done, it's got to be the bottom one, the dichromate. Here's the rest of the answers worked out, by the way, in case you want to see what they are. Slightly different percent compositions. Same exact elements that are present, almost very similar formulas, but again, the percent compositions are just a little bit different due to that difference in formulas. So there you go. There's an example of a wording problem. Here's another one. What if you're given some masses? How can we figure this out? Now we've done an analysis type of problem. Here I'm given a 2.50 gram sample of something. This particular something only contains chlorine and calcium because that's what it says right there on the screen in front of you. And then I can do some further analysis to find out that it consists of 0.90 grams of calcium. So what's the percent composition? All right, strategies on here. Obviously read the question carefully. Try to figure out what it is that you've got going on here. This one's chlorine and calcium. I know how much calcium I have. So now I can figure out how much chlorine I have. Because if I know the mass of the total compound is 2.5 and the mass of the calcium is 0.9, then all I have to do is subtract those two numbers to give me the mass of chlorine. So that's that often by subtraction piece. You can see my work over here on the right. I must have 1.60 grams of chlorine present in this particular compound. And then the last thing I need to do here is to do the percentage, the masses on there. Here's what's nice about this. I don't need to do molar mass for this one because I've already got the mass of the compound. I've got 2.5 grams of compound. I don't know what the formula is, I just know I've got that much. So what's the percent of calcium, what's the percent of chlorine? It's kind of a little bit of a shortcut that's actually even easier than some of the other ones that we've done. So again, you can see my work here. Calcium is 0.9 grams out of 2.5 or 36%. And then the remainder is 1.6 grams out of 2.5%, which is 64%. Again, just a variation on how to do a percent composition, given masses, like I said, from an analysis problem. Okay, what if I have percent composition? How do I deal with this? Well, all right, you can go the other direction. So how many grams of sulfur can you obtain from 137.0 grams of sulfuric acid? This is one of those ones that's a little bit tricky because a lot of students don't recognize that this is actually a percent composition problem, but that's the easiest way to solve this. If I know what the formula is, H2SO4, and then I know how much the total mass is, all I need to do is figure out what the percent of sulfur is in H2SO4, and then I can multiply. So again, it doesn't sound like a percent composition problem, but that's probably the easiest, quickest way to solve this particular problem. So here's what my math looks like as I do it all out. So I'm doing my molar mass of sulfuric acid first, because I know I'm going to need that, 99.08. That's 2 hydrogens, 1 sulfur plus 4 oxygens. I know that sulfur weighs 32.06, so that's my part divided by whole step is the next one. So 32.06 grams of sulfur out of 98.08 grams total gives me 32.769% of sulfur in this particular compound. All right, well now I know that of that 137 gram pile of sulfuric acid, 32.7% of it has got to be sulfur. So now I just do the multiplication. The trick here is to remember that whenever you do multiplication, division problems, etc. with percentages, you have to do the percent as a decimal. So here you can see it right here, that 0.3269. Never multiply by percent as a percent. You always have to move that decimal place back over 2 places. Otherwise your numbers are going to be way off, off by 100 times actually. So here's what I would do, 137.0 times 0.3269, and there's my answer, 44.79 grams. By the way, if you're doing this and you get an answer that's bigger, like 4,479 grams, that just means you forgot to move the decimal place. Back up and try again. All right, one more, I think, percentage composition here. So if I've got aluminum metal, or if I'm trying to get aluminum metal, I should say. This is actually obtained by mining. We get it from different types of rocks, and these are called ores when we get them out of the ground, when they're sources of aluminum. So here's the question, an application question here. Should I use ores that contain aluminum hydroxide or aluminum oxide? Which would be more effective in terms of getting aluminum to be able to do some mining? And so now here I'm talking about 2.50 kilograms of each ore, just as a round number to work with. So what's my strategy here? Again, this is another one of those ones that doesn't necessarily sound like a percent composition problem, but I've got masses and I'm trying to do a comparison based on how much aluminum I can get. So with this one, probably the easiest way, or the way that I would attack this, is to figure out the percent of aluminum in each of those two compounds. Aluminum hydroxide, what percent is aluminum? And aluminum oxide, what percent is aluminum? Because the one that's got the higher percent of aluminum is going to be the one that I want to use. If I've got, 5 grams of a rock that's 5% aluminum versus 25% aluminum, I want the higher percentage. So here's how I would work this out between the two. First of all, start by writing your formulas. Aluminum hydroxide is AlOH3. Hydroxide's a 1-, aluminum's a 3+. So that's where that 3 comes from outside there, right? Symbol charge, cross them down. So the molar mass of aluminum hydroxide here is 78.01. That's 1 aluminum, 3 oxygens, and 3 hydrogens. The percent of aluminum in there is 26.78, that's the mass of 1 aluminum, divided by that total mass of 78.01, so it's about 34.6% aluminum in aluminum hydroxide. How about aluminum oxide? Oh, and I just did that calculation, by the way, while I was at it. If I've got 2.5 kilograms of each ore, I turned it into grams because it's going to make a number that's going to make more sense for me. So again, I do that multiplication. 2,500 grams, you could do it in kilograms if you wanted to, times 0.3459, don't forget, it has to be as a decimal place, and I would get 865 grams of aluminum, or if you did it in kilograms, you get 0.865 kilograms of aluminum. Either one would be correct. All right, let's take a look at taking apart the aluminum oxide. So here it is, the formula for aluminum oxide, Al2O3. Again, aluminum's a 3 plus, oxide's a 2 minus, so you have to cross them down to get that formula. And the molar mass of aluminum oxide is 101.96 by the time we add together 2 aluminums and 3 oxygens. So percent of aluminum is 53.96 grams, that's 2 aluminums, divided by 101.96, the total molar mass, and I get 52.92%. So right there, I can tell you that this aluminum oxide is a better bet. It's got a higher percentage of aluminum than the aluminum hydroxide is. And then when I multiply it against my 2,500 grams, I see the exact same thing, it bears out. In this case, I would get 1,320 grams of aluminum versus 865 grams of aluminum. So again, that higher percentage of oxygen in aluminum oxide is better, and then you can see it that in terms of just numbers wise, I would get more grams of aluminum out of the other one. This isn't 100% true in terms of the actual thing that I would use, but based on percent composition, this is correct. There may be other things that we would use. In fact, I happen to know some of the things about aluminum hydroxide and the way it works out in terms of mining. So if you happen to know something else from outside, like an earth science class, don't panic. This is just based on percent composition. Between these two, aluminum oxide is a better choice. Okay, makes sense? Kind of? All right. So in review, percent composition is pretty straightforward. It's part divided by whole. It's the mass of the element divided by the mass of the whole compound. Don't forget to multiply by 100 to give me the percent, but then don't forget that when you're actually doing calculations with it, that you turn it back into its decimal place. When you're doing these sorts of things, you have to write the formula correctly. You have to balance charges and use subscript numbers. So that's what's going to drive you nuts. Don't just literally list off the names of the elements that are present all the time. If it's asking you about a compound, you have to take that time to make sure that you write the formula correctly first. There's a couple of different types of hidden percent composition formulas or problems. Again, just because the problem doesn't say what's the percent composition doesn't mean that that's not necessarily the best strategy, so be a little bit careful about that. And then again, that last bit, don't forget that when you're doing these sorts of problems that you have to convert percents to decimal places if you're going to do any sort of a multiplication with them. All right, there you go. Percent composition, pretty straightforward calculation. In the next lesson or two, we're going to learn how to kind of use that particular thing, go a little bit further. Have a good one.